get started with material, get through the new material, then we'll use the end of class to do the test. All right. So first off, chapter 1, if you felt like we were covering material at a really, really fast pace, that was the case if you weren't already familiar with the material. So chapter 1 was meant to be a review of the material real quick. So it's probably going to feel like things slow down a little bit from here on out. But you've got to keep up on this homework. You cannot light up on your homework for a second, or you're just going to suddenly fall behind. It's going to turn into an avalanche. You're going to feel like, I'm just done. So you got to keep up with everything. You got to keep working, keep pushing. So now we actually get into calculus material. The rest of that wasn't really calculus. That was just review of maths that you would have come across prior to taking this class. So now we start calculus. In calculus, there's basically 4 main ideas that we're going to cover through all of calculus. And that's it. 4 ideas you need to understand. Those ideas are limits, continuity, derivatives, and integrals. These are the 4 big ideas of calculus. You get these ideas, you get calculus. So this first chapter, because we're not doing a very rigorous course, chapter 2 now, is going to combine these 2 together. So chapter 2 is just going to go over these 2 things, and it's going to do them in a fairly not so rigorous kind of way. And then chapter 3 is focused on derivatives. Chapter 4 is focused on applications of derivatives. Chapter 5 is focused on integrals. Chapter 6 is focused on applications of integrals. And that's how the textbook maps out from here on out. Make sense?
Yep.
So we'll try to give you a brief intuition into what each of these are, and then we'll do a deeper dive into what's actually in this chapter. So let's briefly go over what each of these is. Limits. So first off, let's say that we've got a function that looks something like this. You with me? You notice that it has a circle here at the value 1. There's a circle there. It's f of x is equal to 2 to the power of x when x is not equal to 1. I wrote that backwards. F of x is equal to 2 to the x when x is not equal to 1. And it's equal to 1 when x is equal to 1. You with me?
Yeah.
That's the function I have plotted here roughly.
Okay.
You see it? Okay, so really quick, what is the value of the function at 0?
1.
1. Everyone see what we're doing there? If you plug in 0 as your x coordinate, your y coordinate is 1. The point 0, 1 is a point on the function. Anyone getting lost there?
I got that.
Let's do another one real quick. What about if I plug in the point 1/2? What's the value of the function? Square root of 2, right? 2 to the 1/2 or square root of 2, same thing. So that's roughly square root of 2. What is the value of the function? So let's see. We plugged in f of 0. What was this equal to?
1.
1. Okay. The limit as x approaches 0 of the function says, what does the function get really, really, really close to as x gets really, really close to 0? So as x gets really, really close to 0, the height of my function gets really, really close to 1. When we're looking at the typical functions that we look at, 99.99999% of the points, the value of the function at that point and the limit of the function at that point are the same thing. That's very commonly the case. The value of the function just says, what's the value at that point? The limit of the function says, what's it getting really, 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 really close to? So let's look at another point. What's the value of the function at 1? 1.
Oh.
Right? Notice that there's a hole there.
Yeah.
So the value of the function is 1. What is the limit of the function as it approaches 1? 2. If we go just a teeny bit to the left of 1, we're basically at 2. If we go just a teeny bit to the right of 1, we're basically at 2.
Yep.
And we can get as close to 2 as we want, plugging in values closer and closer to 1. So the limit is 2, the value of the function is 1. So it's only in weird cases like this where the limit of the function and the value of the function are different. You with me?
Yep. Okay.
Now we might have had a function that wasn't even defined on the whole domain. We might have reduced the domain so that this point's not even in there. You with me?
Mm-hmm.
What is the value of the function at 1 now?
Undefined.
Undefined. It doesn't have a value.
Oh, I see.
What's the limit of the function at 1?
2.
Still 2. That's why limits are so useful. They enable us to talk about points that are somehow bad points. It's like, okay, I can't get the value of the function at that point, But maybe there's still some useful information about that point. That point is basically 2, but not quite. All the points around it are approaching 2. Make sense?
Yep.
That's intuitively what a limit is. What's it getting really, 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 really close to, not looking directly at the point, but just looking barely to the left and right.
So you were allowed to put the point 1 there, that 1 point there, because there was no 2, if that makes sense. Meaning you couldn't get, you were not violating the principle that there can't be 2 outlets.
Correct.
I get you now.
Yes. Okay, so that's the idea of a limit. What's the idea of a continuous function? Intuitively speaking, a continuous function is a function that you can draw without picking up your writing utensil. That's a continuous function. This function is not continuous at that point, because I'd have to pick up my pencil to go from this point to this point, right?
Yeah.
Let's draw another one that's not continuous. This function is not continuous at this point. It's continuous from here on out if it goes on to infinity, because from here on out I can draw without picking up my pencil. It's continuous from here backwards, but it's only at this particular point it's not continuous. With me?
So you have to say it's not continuous at that point.
Yeah, it's not continuous at that point. We say the whole function isn't continuous if it's not continuous on its whole domain. We might say it's continuous on some reduced domain. It's like we're defining a new function that only exists on some domain. So we say, restrict the domain, so now this is a part of the function. So it starts right here and just goes. Okay, now it's a continuous function.
Okay.
Okay. That's roughly what continuity is. You can draw without picking up a pencil. There's your intuitive for continuity, intuition. Derivative. Derivatives give us the slope of a function at a point. So what is the derivative of this function?
Just
1. What's the slope of this line?
1?
1,
Yeah.
roughly. I tried to do 1. Oh, sorry, I didn't quite do it, did I? Because my x-axis is weird. But a line where the slope of 1 has a derivative of 1. Derivative gives you the slope at a point. So now if I were to draw some function that looks like this, and say, okay, what's the derivative at 0? The derivative at 0, the slope at 0 is 0. The line that tangent to that point has a slope of 0. Derivatives gives you slope. Good?
yeah.
Just intuitively speaking. I know you don't know how to calculate any of these things yet. That's fine. Just giving you intuition for all of calculus from here on out.
Why is it 0 if the line's still curved?
When it's like this, look at just at that part. So zooming in on just that part of the function. So zoom in really, really close right here. And what does it look like if we zoom in really, really close? It's going to look like this, right? Zoom in even closer, and eventually you can zoom in enough that it's just flat if you zoom in enough on just that point. What does a function look like just at 0? Horizontal line going through it, with a slope of 0.
Does the derivative ever have like roots or exponents in it?
It can. The slope is just a slope. It's just a function just like anything else.
Essentially, you just use the tangent function to do that?
Yes.
Okay.
You take a, you know what a tangent line is? A line that intersects it at only one point. So you draw the tangent line through that point, whatever the slope of your tangent line is the slope at that point.
Okay.
So here's another point. Draw the tangent line to that point. Whatever the slope of that tangent line is the slope at that point.
Which is essentially the cosine divided by the sine divided by the cosine.
It won't be that trivial in most cases. You're thinking about just on a unit circle. That is the case.
Gotcha.
Okay, finally integrals. What do integrals give us? Integrals, roughly speaking, give us the area under a curve. So if I have some curve defined on some domain from this point to this point, there's some curve. When I calculate its integral, it gives me the area under the curve. So areas, slopes, and then you know what continuity and limits are. That's a brief idea of calculus. That's everything that we're covering from here on out. Okay, so let's now jump into the particulars. And we're going to be focusing a lot on slopes today and taking limits of slopes. So to do that, let's go all the way back to, I need some space here, so maybe I'll just redraw this. Okay, going back to good old-fashioned lines. You need 2 points to construct a line. Once you have 2 points, you can construct a line, right?
Yeah.
Okay. Now, one of the most distinguishing features of a line is the slope of a line. So how do we calculate the slope of a line?
Rise over run.
Rise over run. So you look at this distance divided by this distance, and we call that our slope. Okay? We look at our change in height divided by our change in width, and that gives us our slope. Now we typically use a delta y to represent a change in height, and we typically use a delta x to represent a change in width. So this distance from here to here, we call this delta y. This distance from here to here, we call delta x. So slope is change in y over change in x. Rise over run. With me so far?
Yep.
Yeah.
Looking at these 2 points, doesn't matter which 2 points we use, but here's 2 points. So my rise in this case is y2 minus y1. And my run is x2 minus x1, right? You take a difference to find the distance between 2 numbers. If I say, what's the distance between 10 and 3, what is it? 7. How'd you do that? 10 minus 3.
Okay.
If I say, what's the distance between 2 and negative 2, what is it?
4.
4. How do you calculate that? 2 minus negative 2. Or 2 plus 2. 4. So I give you the distance.
The absolute
With me?
value, essentially.
You can take the absolute value of it, but as long as you do it in the same order on here, if they both come out negatives, negatives will cancel out, you'll still be fine.
Oh, that's true.
Okay. So this is equal to our slope, which we typically represent with an m. You with me so far?
Yep.
Now, we could have used x1, we could have used this point and this point to get our line. We could have also used this point and any other point, doesn't matter, just call it xy, instead of just a fixed point, right? So we also know that our slope, m, or y2 minus y1, over, well, here's how I'll say it. I also know that for any other point xy, it's also the case that y minus y1 over x minus x1 is also the same slope. You with me?
Mm-hmm.
Okay. So, looking at this equation now, solve for y. So now y minus y1 is equal to m times x minus x1. You might have recognized that equation of a line before.
Yep.
Point slope form, you're usually used to the y-intercept, right? So how do we get that? We can just write that as y is equal to, do some algebra. M times x is mx. M times negative x1 is negative m times x1. Move the y1 over, plus y1. Constant times a constant plus a constant is just a constant. Whatever all that constant is, we'll just call it b. So then y is equal to mx plus b. And what is that b? What do I know all this has to be?
The y-intercept.
The y-intercept. Because think about it. When x is 0, plug in 0 for x, what do you get? When you plug in 0 for x, you get y is equal to that stuff. Because this term goes to 0. So when x is 0, y is that, or b. Right?
Okay. Yep.
That's why it's the y-intercept.
So I'm a little confused. What with the y that has no
Subscript.
yeah.
So here was 2 particular points.
Yes.
Now I'm saying we don't need to use a particular point. We can use any point xy. So xy is just any point now.
Okay.
And the slope between those 2 points is still the same.
That makes sense.
Okay. So your basic formulas for lines, here's roughly the logic that goes behind it in deriving these equations. Right? You might have seen one more equation. Looking back at this one, you might have seen the one that uses 2 points. So let's briefly, well, doesn't matter. I think these are the ones you use most. We don't spend any more time on. Okay. So there's a quick review of lines. Now let's look into slope. Slope at a point. So that's one of the things that we're very interested in. What is the slope at a point? You know how to calculate the slope between 2 points, right? So here's x1, here's x2. Here's the height at x1, here's the height at x2. You with me? Now our goal is to get the slope at this point. That's what we're trying to do. Now you might say, okay, pick some other point, draw a line through them, calculate the slope of that line, and it will give you an approximation. Right? So, really quick, let's look at that. So what would the slope of this line be between these 2 points? Well, m is equal to the change in height over the change in x. Same thing, just slope. You with me?
Yep.
Yeah.
Now, if we call this distance between x1 and x2 delta x, that's just x2 minus x1. Then, so if we call this distance delta x, then we can write x2 as x1 plus delta x, if delta x is this distance between them. You with me?
Yes.
So I can rewrite this equation this way. I just replaced all my x2's with x1 plus delta x. You follow that? That got me from here to here. Now we're going to do a little bit of algebra in the denominator. We have x1 plus delta x minus x1. X1's cancel out, and we're just left with delta x in the denominator. M is still change in height over change in x. Nothing weird, right? That's what our slope is. You with me so far?
Yes.
Okay, but that is a terrible approximation, right?
Why?
The slope of this line to represent the slope at this point, the slope of the function at this point is more like this. Right? This is a terrible approximation. But what if we used a point even closer? And a point even closer, and a point even closer? What if we used these 2 points? What if we put our x2 here, so that our delta x was really, really small?
It'd be very close.
Then our approximation gets better. You see that?
Okay.
So what happens as x2 approaches x1? What happens as our second point that we choose, we pick closer and closer points? Or in other words, as delta x goes to 0. What happens as the distance between these 2 points I choose gets smaller and smaller and smaller? Then we get a better and better approximation. You see that?
Okay.
And so that is essentially what we're going to do to calculate the slope at a point. We're going to make it closer and closer and closer and closer and closer. We're going to make it arbitrarily close. That's what we're going to do to get the slope at that point. You with me? So how do we do this? Let's see what I say. The idea. What's the idea? The idea is the slope of our function f at x1 is given by the limit of our slope as our delta x goes to 0. That's the big idea. Here is the slope of our function between 2 points. Just this part of the equation, right? As delta x gets closer and closer to 0, then we get a better and better approximation at that point. So the whole idea is the slope at x1 is given by this equation, the limit as delta x goes to 0 of delta y over delta x of our slope. That's the big idea. You follow that big idea?
Yep.
So let's do this and see what we get. And we can actually calculate these things, surprisingly enough.
Okay.
Yeah, I'll walk you through it. It's not nearly as complex as it might seem. In fact, it's much, much easier than trying to just pick a really, really close point and approximate yourself. So let's go over it. So here is some function, f of x is equal to x squared minus 1. Roughly plotted right here. I want to figure out what the slope of this function is at x equal to 1 and then at x equal to 2. And we'll do both these as examples. You with me? Okay. So I am trying to calculate the limit as delta x goes to 0 of f of, what's my x1? I'm plugging into this equation.
1 or 0.
x1 is the point where I'm trying to find the slope at. Where am I trying to find the slope at?
1.
1. So of 1 plus delta x minus f of 1 all over delta x. So limit as delta x goes to 0 of the slope of my function, where my left-hand point is 1. Does everyone see how I just plugged into this equation right here? I just replaced the x1s with the actual point we want now is 1. Notice x1 was the point we wanted the slope at up here. Down here, I want to find the slope at 1. I want to find the slope at this point on this parabola. Good?
Yep.
Okay.
Okay, so now we're going to calculate this. Before I take the limit, I'm just going to work, well, no, we'll do it tediously the first time we do it. So then the limit as delta x goes to 0 of, what is f of 1 plus delta x?
1 plus delta x squared.
You're plugging it into your function, right?
Yeah.
Oh, I see.
So it's 1 plus delta x squared minus 1. That's the first part. So I plugged in this piece right there. Minus 1 squared minus 1. All over delta x. You with me?
Yep.
Okay, simplify. So I'm looking for the limit as delta x goes to 0 of, let's see, 1 plus delta x squared. What are we going to get? Well, 1 times 1 is 1. We'll have 1 times delta x and then delta x times 1. So we'll have plus 2 delta x. And then we'll have plus delta x squared. That's this term, squared out.
Okay.
Then I'll have minus 1. And then I have minus 1 minus 1 is just 0. So we're done. This part goes to 0. You see that?
Yeah.
Yep.
Okay. All over delta x. Good? Have I lost you yet?
Nope.
Okay. More simplifying, we have 1 and negative 1 there.
Mm-hmm.
So let's rewrite it one more time. We're looking for the limit as delta x goes to 0 of 1 and negative 1 go out, so we have 2 delta x plus delta x squared all over delta x. You with me?
Yeah.
Can we simplify that anymore?
Yes.
What can we do?
You can divide by delta x.
Yeah, we can factor a delta x out of the top and cancel them out with the bottom.
Yep.
You see that? Let me rewrite it one more time before we do that, in case we're missing what I'm saying. Delta x goes to 0 of, factor delta x out of the numerator, and you're left with 2 plus 1 delta x now, because this was delta x squared, all over delta x. You see that? Cancel out delta x in the numerator with the denominator, so this is equal to the limit as delta x goes to 0 of what?
2 plus delta
2 plus delta x.
x.
What does that equal as delta x gets closer and closer to 0?
It gets closer and closer to 2.
Just 2. You did it. You just calculated a derivative and a limit. Knocked off 2 of those things.
Okay.
That's what we're doing.
The slope of that point is 2.
The slope of this function at this point is 2. If you draw a tangent line through that point, it will have a slope of 2. If my picture didn't lie.
And the limit's also 2?
The limit of this expression is 2. The limit of this, as delta x approaches 0, is 2. We didn't graph what this thing looks like. We graphed what f looks like.
Yeah.
This is the slope of f at 1. This is f. We just graphed f. So the limit of the function at 1 is 0.
Yeah, that's amazing.
We did not calculate the limit as x approaches 0. Notice we don't have a delta x there. Of f of x is equal to, oops, as x approaches 1, is just 0. That's just a function right here. Two very different things that we're talking about.
Okay.
All this was calculating the slope. That's not the same thing as the limit of the function at that point.
So
We
you,
calculate a different limit. We calculate the limit of this big looking thing. We did not calculate this limit. Those are two very different things. We calculate the limit of a slope of a function, not the limit of a function.
but you still use the limit to get
You
this.
use limits left and right. We'll use limits for integrals, we use limits for derivatives, we use limits to show something's continuous.
Okay.
So you use limits all the time. Two separate ideas. There's taking limits, and then there's calculating slopes at points. You use limits to calculate slopes at points, but you use limits for lots of things. Slopes at points is just one of the things you use limits for.
Okay.
Okay? So let's do it again.
Yep.
So this time, I want to calculate the slope of this function at the point 2, right? Only difference, replace that one with the 2. Probably shouldn't have replaced or erased all my algebra because it's going to be basically the same algebra, but now with the 2 in there. You ready?
Yeah.
Okay, so now I'm just going to work with the inside expression, rewrite the inside expression, and then calculate the limit when we're done. So I'm not going to keep rewriting this limit thing over and over again.
Okay.
But we're still taking the limit. Okay, so this is the same thing as taking the limit of, I won't write equals. We'll just rewrite this. So we have, not f now, let's plug this into the function.
2 plus delta x squared.
2 plus delta x squared
Minus 1.
minus 1, all minus
Delta.
2 squared
plus
minus
2
1,
squared minus 1.
Yeah.
right?
Okay.
All over delta x. Well, that's going to be the same thing as, let's see, 4 plus 4 delta x plus delta x squared, that's expanding this out, minus 1, minus 4 minus 1 is 3, so minus 3.
So then you just left with
All over delta x, which is equal to,
4 delta
4
x.
goes out there,
So,
delta x here and 1 here cancels out with that, so we're left with just 4 plus delta x. You see all that? Or is that too much algebra? Bit too
Be
much?
nice to see it.
Okay, so I'll just get rid of the 4, the negative 1, and the 3 in one go. Okay. See that?
yeah.
Now factor delta x out the numerator, cancel it out with the denominator. So now we're looking for the limit as delta x goes to 0 of 4 plus delta x, which is equal to 4. There we go. The slope at 2, if we drew a tangent line through it and carefully measured it, would be 4. Got it?
Yep.
Cool. So that was my way of coming at this material. The author had another way, so now we'll cover the author's way. Doesn't hurt to cover the same idea twice. The author decides that he's going to start with what we call Galileo's law. Galileo's law is that when you have an object in free fall, and you let it fall, then if we measure it in feet, its position after t seconds is 16 times t squared. What do I mean? I mean, if I drop this thing and I let it fall for 1 second, it will have fallen 16 feet. If I let it fall for 2 seconds, it would have fallen, 2 squared is 4 times 16 is 64, it would have fallen 64 feet,
Oh, well. Roughly?
roughly. This is ignoring air resistance.
But even, so 16 feet is, I don't know if they ever made feet like equal to how gravity falls perfectly, or is that?
It's a rough approximation. If you did it, the one I'm used to in physics and the one that we'll use in physics is it's actually, we would write it with 9.81 over 2 t squared. That's for meters.
Okay,
That's what it roughly is for feet.
gotcha.
Anyways, so just a fact of the universe, Galileo went out there, measured a lot of things, and he found this seems to be the case. With me? Okay, so we're going to play with that equation and discover some things. Now, before we do, we need to understand the concept of average speed. Average speed. If I say that you went 300 miles in 5 hours, what was your average speed? 60 miles per hour, right?
That's like,
If you go 300 miles in 5 hours, you average 60 miles per hour. Now, there could have been points where you were going 100 miles per hour and other points where you were going 20 miles per hour, but your average speed was 60 miles per hour. Distance over time gives you average speed. Good? Okay, pretty intuitive. Okay, so with those two things in mind, we're going to now answer some problem. A rock breaks loose from a cliff, so it's on the bottom of some cliff. Rock breaks loose from the cliff. What is its average speed during A, the first 2 seconds of its free fall, and B, during the second of its free fall? Because the rock speeds up as it falls. So let's focus on A for a second in case that second is throwing you off. what is its average speed during the first 2 seconds of its fall? That's what we're going to calculate. We need to do distance over time.
Well, that's easy.
So you plug in.
That's easy.
It's 32, right?
Yeah, it's going to be 16 times 2 squared minus, so our endpoint minus our start point. Our start point was 16 times 0 squared, or 0, right?
Okay.
Because that's how you calculate distance, your endpoint minus your start point.
Get the delta, right?
Yeah, divided by, and our change in time was 2 seconds, or 2 minus 0. Right? And what's the big old answer? 32. Quick algebra there. Wonderful. Feet per second. Won't be as worried about units in this class as we will in physics. Physics, I'll dock you every time you forget those. Okay, so 32 feet per second. That was its average speed falling. With me? Okay, now let's calculate its average speed during the second of its fall. So we ignore the first second. So the rock falls for 1 second. I say starting there, over the next second, what's its average speed? Because objects speed up as they fall. It makes sense objects speed up as they fall, right? Okay, so let's calculate that one. I don't know if I'll need this space. So this was 32. This one here, now, let's calculate. How do we get that? It's the distance at 2 seconds minus the distance at 1 second over our difference in time. The second minus the first second.
Okay.
Same basic logic we've been using the whole time. Okay, so what do we get here now?
48.
64 minus 16 is 48 divided by 1. 2 minus 1 is 1. So 48. So well, yeah. Make sense?
Yes.
No?
Why is it going faster in 1 second than it was in both seconds?
No. Its average speed, look, take my average speed as I start out slow and I speed up and I speed up and I speed up, and you do that for 2 minutes, right?
Okay.
Now I say ignore my time, ignore it for the first half of my running, and just count the second half when I was running faster. My average speed will be faster.
Okay.
It's speeding up as it falls. It starts out slow for the first second, it's speeding up. That's the first second. During the second second, it's going a lot faster. It covers a lot more distance.
Okay.
So its average speed over the whole 2 second duration is less than its average speed during just its fastest portion of its fall. Okay. Make sense? Maybe do one more quick one to see if we got it. What's its average speed during the first second of its fall?
Just 16.
Just 16. 16. So this was its average speed during the first second. This was its average speed during the second. This was its average speed over both seconds.
Okay.
Okay. Now we're going to do the problem of, okay, that's average speed. Now let's find the exact speed. Let's find the exact speed of the rock after it's been falling for 1 second. And let's find the exact speed of the rock after it's been falling for 2 seconds. And it's going to come back to the same idea of taking a limit.
Okay.
You with me? So, average speed is delta y over delta t, right?
Yeah.
If we want instantaneous speed, if we want the speed at a time, then we want the average speed between 2 points really, really, really close together. Same thing we were doing over there with slope.
Okay.
Same idea. So my average speed is equal to the distance that we've gone after my start time plus the duration minus the distance that we've gone at my start time. Reference that equation right here. Exactly what we have written up there, right? This was my f of 2 seconds. minus f of 1 second, where my duration was 1 second. You see how this and this are saying the same thing? F of start time plus my duration minus the distance at my start time all over my duration. Good?
I think so.
Okay. Now, for some reason, in newer calculus textbooks, newer meaning after the year 2000 or whatever, I'm not sure when this happened, we loved sticking h's in there for these delta t's or these delta x's. So where I used a delta x over here, the author is going to use h's. Where we had delta t here, the author replaces it with h's. I don't know why this is a convention, but it is now a convention typically used in Calc 1 classes. So this is what you're going to see in your textbook. This is what you're going to see when you all go to college and you go take calculus. This is the stuff you're going to see. Okay, so I'm just going to replace those delta t's with h's.
Okay.
That's all I did, rewriting it. Good?
Mm-hmm.
Okay, which is equal to, now plug in for our particular function. So this is what is in general, but we have our given function up there, so here's what it is for our particular function.
Okay.
You with me?
Yep.
Don't lose track of the problem. We're trying to find the speed of the rock at t equal to 1 and t equal to 2. So here's what it is at t equal to any t you give me. I'm just going to come up with a formula for any t you give me, and then we'll plug in 1 and 2 and see what we get. You with me?
Mm-hmm.
Okay. Now, just because the author went through the work of doing it, we'll write some numbers out here. Now, the author's saying, look, if you use smaller and smaller h's, you can get an approximation from this equation, right? So if I let t naught equal 1, so we're saying we're looking for the speed of the rock at t equal to 1. So if I look at the speed for the rock at t equal to 1, and I let h be an entire second, then we get 48.
Okay.
Which is the exact, this number right here that we got.
Which is the average speed.
Which is the average speed, but remember what we're looking for. We're looking for the speed at t equal to 1, right? We're going to find that by looking at the distance at t equal to 1 and the distance at a later time and just saying the average speed. And then we'll make that later time closer and closer and closer to our start time. That's ultimately what we're going to do. So if we say, we'll look at its position at t equal to 1 and t equal to 2 when h is 1, so our duration is 1, then the average speed looks like it's 48.
Okay.
But if we lower our h, so now we look at t equal to 1 and t equal to 1.1, so our interval now is just 1/10 of a second, and we calculate our average speed, we get 33.6. Okay, now if we let t equal to 1, and we use t equal to 1.01, so our interval, our duration now, is just 100th of a second, and we calculate the average speed, we get 32.16.
Okay.
And if we make our interval 1/10,000th of a second, then our average speed is 32.00016 meters per second, or feet per second, sorry. So as h gets smaller and smaller, it looks like our average speed is getting closer to 32. Does that make sense?
Yep.
Similarly, if we were to start at the point t2 and try and calculate the average speed there, we'd get 80, 65, 64, 64.00016. Same thing. You with me?
Mm-hmm.
Now those are all fine and dandy approximations, but now we want to try and get exact. So you could do it this way, see what number we're getting closer and closer to, and maybe figure it out that way. But that's a lot of work, we don't want to do that. So now let's do it how we did it before. So starting with this equation, I rewrote it right up here, except I guess I did a little bit of algebra. I expanded this out.
Why?
How?
So this to up here, all I did was expanded this out.
I see.
Oh, yep.
So the 16 is still there. T naught squared plus 2 T naught times h plus h squared minus 16 T naught squared. With me?
Yeah.
Okay. Some more basic algebra. Just distribute the 16 through. 16 T naught squared plus 32 T naught h plus 16 h squared minus 16 times t naught squared.
I missed why did we say t naught? What does that stand?
Initial time. Sorry. That is a convention used in physics. Your initial time, you use t naught. Just means your start time.
Oh.
And yeah, don't say t sub 0, I say t naught. Convention, once again, from physics. Sorry. A lot of my physics language is coming through because it's a physics problem.
That's cool.
But yeah, make sure I clarify stuff like that if it sounds like I'm talking funny. It becomes so natural. There'll come a point where you don't even notice it. Okay, anyways, so we got from here to here. Okay, from here to here, what am I going to do? I'm saying, look, 16 t naught squared minus 16 t naught squared. Those go out, right?
Yeah.
So now I'm left with 32 times t naught times h plus 16h squared. I'm left with just this portion, right? But I factor out h.
Okay.
You with me?
Yep.
Now h cancels out top and bottom, and we get this expression right here.
Okay.
Okay. Now, what were we looking for?
Limit of 1.
We are looking for, first off, the limit as h approaches 0, but we need it for two different points. We said when t naught's equal to 1 and when t naught's equal to 2.
Yep.
So we're looking for when t naught's equal to 1, so we're looking for this, 32 times 1 plus 16 times h. And we're also looking for this, the limit as h approaches 0 of 32 times 2 plus 16 times h. Those are the two values that we're looking for. Coming back to where this problem started.
Okay.
At time 1 and at time 2, what is the speed? Calculate the limits. What do we get for this limit? 32. As h gets closer and closer to 0, what did I write here?
I think that's supposed to be 16.
Sorry, that was probably real confusing. Okay, everything up there looks normal now, right?
Yep.
Okay, so as h gets closer and closer to 0 on this expression, what do we get?
32.
32. As it does on this expression, what do we get?
64.
Perfect. Which is exactly what we saw these two numbers were trending towards.
That's really cool.
It is really cool.
Who discovered this?
Newton. Okay, so there we go. We've done a couple problems with these.
Put the camera down.
Oh no.
I just realized I missed that part right there.
Ah! Well, thank you for pointing it out late, Jeremy. That's going to be reflected in your test score. Okay, so don't have any of the purple. Should always do my squigglies. Problem is that I need to remember to do my squigglies. To have my squigglies remind me. It's like how worthless a remember all is in Harry Potter. Hey, you've forgotten something. Well, thanks. Makes no sense. Okay. So, hopefully, when you're at home, you can reconstruct this algebra over here that we did. Right?
Are we doing that in our homework?
This, simplifying to this, I have no clue. I don't do your homework problems, you do. Simplifying to this, and then from this equation, we just calculate the limit here and here. First case, when t naught was equal to 1 second. Second case, when t naught was equal to 2 seconds. So that's all we did. Hopefully, got enough in the video that that can make sense. Okay, so moving forward. Average rate of change. Oh, I guess we have a definition now. The average rate of change, before we were talking about average speed. Average speed is the average rate of change of distance with respect to time. So it's just a particular type of average rate of change, right? The slope of a function, when we do the average slope between 2 points, between here and here, if I draw a line like this, the slope of that line is the average slope between those 2 points, or the average rate of change between those 2 points.
Yep.
On average, going from here to here, on average, we went up 5 every 2 that we went over. Or 4, 1, 2, 3, 4, every 2 that we went over. So the average rate of change between this point and this point was 2. Make sense? So average rate of change, just something a bit more general than just talking about slopes or just talking about speeds. A speed is an average rate of change. The slope is an average rate of change. Okay. So the average rate of change of some function y equal to f of x with respect to x over the interval x1, x2, so you make that the domain that we're talking about, is, that portion of the domain is what we're talking about, is just the change of y over the change in x. Or in other words, it's the height at x2 minus the height at x1 over x2 minus x1. Right?
Yeah.
Or using the author's notation, it's x1 plus delta x, or h, minus f of x1 all over h, where h is not 0. We've just done this 3 times, right?
Yeah.
Remember that x1 plus h is x2, right? x1 plus our interval that we're doing it over gets us to the next point that we're using, x2.
Okay.
Yep.
When we were looking back over here, we had, that's exactly what we did from here to here. We replaced the x2 with x1 plus delta x. And remember, the author uses an h instead of delta x. H is always a stand-in for delta x. So, this is the case. Any questions on this? Why when h is not 0? We didn't really give any mention to that.
So it's
Why do we ignore the case when h is actually 0?
It's undefined.
It's undefined. That's why we're using limits. Remember, limits have this magic ability to talk about really, really close to a point, but not quite the point.
Again, it is. It's so confusing.
It's really, really close to. It's arbitrarily close to. It's not within 0.00001. No, that's a massive distance. It's arbitrarily close. Okay. So, really quick labeling some things on here to make sure that this makes sense. Here's our x1, here's our x2. The distance between them is what the author calls h. So this point could also be written as, this is the same point as x1 plus h, comma, f of x1 plus h. That point and that point are the same things, and then I think that equation is pretty obvious where it's coming from. Any questions with any of that? Just a slope. Rise over run.
Why do they fuss over the fact that it can't be 0?
You can't divide by 0.
Well, why? Because obviously it works.
No, it never works. We did not divide by 0. We divided by a number arbitrarily close to 0. We did not divide by 0. You can't divide by 0. Dividing by 0 is undefined.
I understand the argument.
I don't have time to... It's undefined the same way that if I said, what's the definition of blah? And I said, blah means anything you want it to be. That's not a definition. It doesn't tell me what blah is. You make blah meaningless. I can make, if you allow dividing by 0 to give you a number, I can make it give you any number now. It's broken. So you can't divide by 0 and assign that value.
That's interesting. Okay.
Okay. So, moving on now, this. Okay, so let's do another one. See another example of these. Let's find the slope of y equals negative x squared at the point 2, negative 4. Give you a rough idea of what this thing looks like. It's a parabola, but it's a parabola pointing downwards. So, look something like that. So at 2, negative 4. At that point. We're looking for the slope at that point.
Okay.
You with me?
Yep.
All right, so that's what we're looking for. Notice one thing right out the door. Just estimate really quick what you think it should be roughly. Spitball. Just throw out a number.
-2.
-2. Okay, good. So -2, roughly somewhere in that ballpark. Keep track of the fact it better be negative, and it's kind of steep. It's definitely steeper than 1. Okay, so -2, not a bad guess. I'm just erasing the picture, so I want you to get some basic information that you can from the picture. So from the picture we said, it seems like it should be roughly -2-ish. Okay, with a terrible picture, but good enough. Okay, so let's actually find this in. So, how do we find it? What are we looking for?
You look for the slope of the line.
Tell me exactly what's right.
F. And then
Looking for f of what?
X.
2 plus
2 plus our small little interval past 2, h,
Minus F2
minus f of 2
over H.
over h. Wonderful.
Okay.
Okay.
Just plugging in for the formula, what do we get?
You get 2 plus H, negative 2 plus H squared minus negative 2 of H.
2 of h.
No.
Minus
2 squared. Over H.
2 squared, like this. Let's see, minus, just to keep it really clear, negative 2 squared, all over h. Okay,
Okay.
just plugged in, right?
Okay.
That's all we've done so far. I want to make sure you guys can do all this.
Good try.
Okay.
Okay, algebra means that first term. What does this turn into when we expand out the squared?
Negative 4.
Oh, you're going to do the negative 2?
Minus 2h minus h squared.
Minus 4h, right? Let's keep the negative out because I think that might be throwing people off.
Yeah.
Yeah.
Negative, let's square it first. 2 times 2 is?
4.
That was quick. And then we have 2 times h, and h times 2 gives us
4H
4h. And then h times h gives us,
squared. H squared.
okay, minus, well, give me this whole thing now.
Plus 4.
plus 4.
Wonderful. All over h.
Okay.
Okay, now we can distribute the negative. Negative 4 goes out with the 4, so I won't bother with that.
Okay.
So we get negative 4h minus h squared over h,
Uh-huh.
which is equal to,
H parentheses negative.
h's go out top and bottom, just,
Yeah,
we'll just skip to that. We good?
that works.
Yeah.
Now, what are we trying to calculate? We're trying to calculate the limit as h approaches 0 of this whole thing. So, of this whole thing is the same thing as this whole thing, which is equal to what?
Negative 4.
Minus 4, which is ballpark what we thought roughly it should look like from the picture. There, we just calculated the slope at that point.
Okay.
Okay,
Good?
that works.
All right. Okay, now focusing a little bit more on limits. Let's look at a really funny function here. So we're stepping away from slopes for a second now, focusing on limits. We just really switch from 2.1 to 2.2, going from here to here. Just so it feels like massive context switch, it is. Switching gears now, focusing more on just limits and not limits of slopes. So everything we were doing it before, we were doing limits of slopes, limits of slopes, limits of slopes. That's what we did over and over again in different ways. Now we're just looking at limits, a limit of a function. Okay, so let's look at a funny looking function. Let's look at f of x equal to x squared minus 1 over x minus 1. Now from all your homework problems, tell me what the domain of that function is.
All the real numbers except 1.
Anything but 1, right?
Yep.
Okay.
You slaved away for hours to figure that out. I remember. You texted me. So anything but 1. So this function isn't behaving nicely at 1. If I tell you what is the value of the function at 1, you can't get the value of the function at 1. Make sense?
Yes.
Okay, but let's see what we can understand about this function. Let's plot some points and see if we can piece something together. Ignore my table here for a second, and let's just plot some points. All right? What do you get when you plug 0 into that thing?
Negative
1,
1.
right?
Yep.
Okay, so here's a point on there. Okay, plug negative 1 into there, what do you get?
2.
Try again.
0.
0. The numerator is 0,
Oh.
and the denominator is negative 2. 0 divided by negative 2 is still 0.
Okay.
Okay, let's go ahead and plug 2 in there.
3.
3.
Yep.
When you plug in 2, you get 3. What does it look like this thing is producing? A line? A straight line?
Yeah.
Yeah.
So it kind of feels like it's producing a line here, which is what it is producing. So your intuition's good. Except at 1, we've got a hole. We don't have a point there. Right? Because remember, we can't plug 1 into this.
Yeah.
So here's what that function looks like. Hole at the point 1, everywhere else we're fine.
Okay.
Okay, question. What is the limit of this function as it gets closer and closer to 1?
2. Yeah, 2 makes sense.
2. Yes. What does it get closer and closer to at 1? What's my height here? 1. What's my height here? 1.5. 1.9. 1.99. 1.9999999. I'm getting closer and closer to 2. We're coming out the other way. What's my value here? 3. 2.5. 2.1. 2.01. 2.001. And if you were to actually plot some points in here, so when you plug in 0.9 for x, you get 1.9. So if we look at a point just to the left of 1, we get 1.9. If we look at a point just to the right of 1, we get 2.1. Okay, let's get even closer. Let's look at 0.99. What do we get? So a point barely to the left, we get 1.99. If I look at a point barely to the right, I get 2.01. Get absurd with it. Let's look at 0.999999. That's a point barely to the left of 1. What do we get? Basically 2. Plugging a point barely to the right of 1, what do we get? Basically 2. So this thing looks like it's getting closer and closer to 2. Right?
Yep.
And it is getting closer and closer to 2. Do we actually calculate this one? We can just calculate it real quick to show you that that is in fact what is happening.
Okay.
And how do we look at that? We say, what is the limit as x approaches 1 of this thing? X squared minus 1 over x minus 1. It's kind of similar to the problems we've already been doing. We're kind of jumping ahead in the book, but let's just see it now here so you don't think anything weird's going on. Well, this is equal to the limit as x approaches 1 of, what can we do with a difference of squares?
You can factor it.
You can factor it. Everyone who took discrete math, Peter,
Yep.
that better be the first thing that comes across your mind. We did that so much it's absurd. Oops, that's mine.
X minus 1.
Ah, now what can we do?
Cancel it out.
We can cancel top and bottom. So this is equal to the limit as x approaches 1 of x plus 1, which is equal to what? 2.
Yep.
So you'll notice that oftentimes the trick with calculating a limit is to get that pesky thing that's going to 0 out of the denominator. That's often the trick. Notice the problem with all the problems we were doing over here, we had an h in the denominator. We needed to get that h out. Still had the h in the denominator, still had the h in the denominator. Oh, we got the h out of the denominator. Now we can look at what happens as that thing goes to 0. We had here an x minus 1 in the denominator. Can't do it because as x approaches 1, that's getting closer and closer to 0. Still had it in the denominator. I got it out of the denominator. Now we can see what's happening.
So this only works if the numerator and the denominator have the variable?
It's just a common trick. It's not a rule. This is what you always do. It's a common way that these types of problems are solved. It's a common thing to first look for when you're trying to solve a problem.
So sometimes it's not useful. In fact, probably a lot of the time.
Typically the reason you can't calculate the limit is because your denominator is going to 0. And so you need to come up with some way to make so your denominator is not going to 0. And then you can take your limit. Typically that's what's happening.
Okay.
Okay. So there we go. That was it with that. Let's look at whatever I have in green here. Oh, that was... Okay. So let f of x equal x plus 1, g of x equal x squared minus 1 over x plus 1, and h of x equal x squared minus 1 over x plus 1 when x isn't equal to 1, and let equal 1 when x is equal to 1. You understand these three functions?
Yep.
Let's briefly plot them. All right, first one, x plus 1, that's easy. That's this line. All right, let's graph this one. X squared minus 1 over x plus 1. Easy, that's this line, except for we get rid of that point. That's one we already have plotted. So if I fill in that point, I've got this function. Get rid of the point, I have that function.
Not necessarily. It is when it's x minus 1 in the denominator, not x plus 1.
Oh, did I write that wrong? Thank you. Good catch. So either I wrote those wrong or I wrote that one wrong. Maybe that was an x minus 1, I don't know. What I have there works, who cares? Might be different than the example problem your book did not. That doesn't work. No, it's the same as this. Anyways, so x plus 1, that's this line when we fill in that point. X squared minus 1 over x minus 1, that's this line when we don't have that point. You with me? Mm-hmm. And then if we plot h, it's the same thing there except for at 1, we plot the point 1. So we put a point here. Here's h.
Okay.
So you have what those three look like in your head. Okay. So now let's calculate some values. What is f of 1?
2.
Everyone see how she's doing that quick math?
Yep.
Remember that the purple, oh, it's over here. One of these is very good. This purple. All right, so this was 2. What's g of 1? Undefined, can't do it. What's h of 1?
1.
Follow all that?
Mm-hmm.
All right. Now, what's the limit as x approaches 1 of f of x?
Just 2.
Just 2, right?
Okay.
As x gets closer and closer to 1, that whole sum gets closer and closer to 2. What's the limit as x approaches 1 of g of x?
Just 2.
That's what we calculated over here.
Okay.
What's the limit as x approaches 1 of h of x? We now have that drawn right here.
It's 2. 2. That's right.
2 still. So notice that even though the value of each of those functions was very different at that point, they still had all the same limit at that point.
Okay.
Right?
Okay.
So they're all getting really, really, really close to having 2 at that point. Maybe they do, maybe they don't at that exact point. But really, really, really close to that point, they all have the value 2.
Okay.
So bizarre.
Well, so we'd say somehow these functions are all behaving the same around 2. Maybe not exactly at that point, but around 2, all these functions are behaving identically. That's another way to say it. Okay. Note. What's our note here? If f of x is equal to x, I want you to say it. All right, so let's look at the function f of x is equal to x. Pretty simple function here,
Yeah.
Yep.
right? What's the limit as x approaches c of that function?
Just the same thing.
Just c.
Yep.
Yep. Nothing fancy, right? As x gets closer and closer to c, f of x gets closer and closer to c, because f of x is just equal to x.
Okay.
Good?
Mm-hmm.
Let's look at another one. So now say f of x is equal to k, a constant. Remember what constant functions look like? Just a horizontal line. Where's my chalk? If I were to graph the function y is equal to 3, looks like this. Just a vertical line to the point 3.
Okay.
Right? So, if f of x is just equal to some constant, then what is the limit as x approaches c of f of x? It's just a constant, right?
Yeah.
That makes sense?
Mm-hmm.
Pick any number looking at this function. Here's a function, y is equal to 3, right? Right here. What does a function approach as x approaches 1? So here's 1. What's the limit of this function as x gets closer and closer to 1? 3.
Yep.
What's the limit as it gets closer and closer to 10? 3. What's the limit as it gets closer and closer to negative 3? 3. The function's always 3. So if a function's a constant, it's just always that constant, and it's always getting closer and closer to that constant, because it is that constant everywhere.
Okay.
Okay. I don't know why I left space there. I obviously thought I was going to be writing something. But I don't know what it is, so we'll move on. Move on to limit laws. Limit laws. Unfortunately, we don't really have the tools to prove any of these right now. So most of them you just have to kind of take my word for it, but I think it will appeal to your intuition. So let's just go over it. First here, okay, if L and M and C and K are real numbers, so those are just stand in for real numbers, such that the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to M, then all these things are true. But let's make sure we understand what these numbers are. What is L? Tell me in words what L is. It's the limit of f as x approaches c. So if we were to plot f really quick and plot g, maybe they'd look something like this. Maybe f would look something like this, and maybe g would look something like this. So here's f, here's g, and maybe c is this point right here. Then this right here would be L, and this right here would be M.
Okay.
And maybe they both happen to have holes here. Who knows? So they don't actually have the point there. Maybe they do, maybe they don't. We don't know. But it doesn't matter. The point is, some functions we don't know anything about them. All I know is that as x approaches c, f of x approaches L. With me? And as g of x approaches c, as x approaches c, g of x approaches M. Whatever it is. Talking very abstractly, we're not talking about any particular functions, we're not talking about any particular points. Good? Okay, so if that's the case, then these 7 rules hold. The limit of a sum of two functions is equal to the sum of the limits of the two functions. The way we typically say that is the limit of the sum is equal to the sum of the limits. Maybe write this out one more way so that you can see exactly what happened here, and then with the other ones, it won't be so confusing. The limit of a sum is equal to the sum of the limits, which is the same thing as that.
Yep.
Okay.
You follow that?
Yeah.
Another way you can kind of think about that is like you can distribute a limit over a sum. Good? Okay, next. The limit of a difference is equal to the difference of the limits. This basically just falls from this almost.
Okay.
Good? Next, the limit of some constant times your function is equal to a constant times the limit of your function. In other words, you can pull constants out of limits. Let's look at a concrete example of that one real quick in case that seems weird. Let's look at the limit as x approaches 2 of 2 times x squared. What this is saying is this is also equal to 2 times the limit as x approaches 2 of x squared. You can pull constants outside your limit. That's what it's saying.
Okay.
Make sense? Okay? And then a limit of a product is equal to the product of the limits. A limit of a quotient is equal to the quotient of the limits as long as the bottom number doesn't approach 0. Right? As long as the limit of g of x is not equal to 0, then this works. If it equals 0, you got to do some more manipulation possibly to solve the problem. Right? Like over here, we couldn't just do it.
Okay, so let me get it straight. M is as x.
M
close to
is
C.
as x approaches C, what g of x gets closer and closer to.
So M is what g of x is as x gets closer to C.
Yeah, M literally is a short way of writing this whole symbol.
Okay, I just.
Yep.
I'm with you.
Okay, next. The limit of an exponential is equal to the exponential of the limit. So what's that saying? That's saying if we have the limit as x approaches 2 of x squared, that is equal to the limit as x approaches 2 of x all squared.
Okay.
Make sense?
Yeah.
Okay, and then finally the last one is just with roots. The nth root, if you take the limit of a root, that's equal to the root of the limit.
What does that mean?
So if you have the limit of the square root of x, that's the same thing as the square root of the limit of x.
Okay.
You can pull the square root all the way out, or shove the limit in, however you want to think about it. And the square root, notice that square root is also the same thing as x to the 1/2. That's the same thing as square root of x.
Is there any importance in using brackets instead of parentheses?
Now, parentheses, brackets, and curly braces used inside an expression all do the exact same thing. We just use different symbols to help us keep track of which goes with which. So, since I don't want to get any confusion with the round parentheses I'm using on the function call, I use square brackets. But replace my square brackets with parentheses and we're still in the same boat.
With the exception.
So I'll arbitrarily switch between them.
With the exception of referring to sets.
Yeah, there are exceptions. I could be using parentheses to talk about a point. 1, 0, I could use that to be talking about a point. That's not an algebraic expression. And yeah, I could be using this to talk about a set. That's not an algebraic expression. I'm saying in algebraic expressions.
Okay.
Yes. Yeah, we use a lot of the same symbols for a lot of different things, so it can get confusing. All right, let's do some examples now. First one, let's look at the limit as x approaches c of this function. X cubed plus 4x squared minus 3. What is it equal to? Well, we'll do one the tedious way, and then from there on out, we'll stop with the tedious way.
Okay.
So we can say that this is equal to the limit as x approaches c of, and we can break this into 3 limits, of x cubed plus the limit as x approaches c of 4x squared plus the limit as x approaches 3 of negative 3, right? We can break it up into 3 pieces. Oh geez, I'm not going to use all the rules. That would be a lot of writing. I think you can see where all of these would go though, right? So ultimately, what's this one going to equal?
C cubed.
This one's just c cubed. C squared. Sorry, this equal is not applying to this. Maybe I'll write over here. So it's still equal to, when I evaluate this limit, we just get c cubed. When I evaluate this limit, I get
4c squared.
4 times c squared, yep. And when I evaluate this limit, I get
Negative.
negative 9, right? No! What? That's some weird logic I'm throwing out there. No, it's just negative 3. The limit of a constant is always just a constant.
Why do you have x
Okay.
approaches 3?
What?
Oh!
Negative?
Thank you.
Okay.
Thank you,
Oh,
thank
I thought that was.
you. Even if it was 3, it doesn't matter what it is.
Right?
But yeah, you're right. I should definitely not have had that in there. Minus 3. C cubed plus 4c squared minus 3. That's what it equals. Just take the limit. Alright, let's do another one. Let's calculate the limit of this thing now. Just tell me what it is.
Basically replace all the x's with c's.
That's it. It's that simple. C to the 4 plus c squared minus 1 all over c squared plus 5.
Do you have to add anything to that, like saying that c can't be the square root of 5 or something like that? Or, oh wait, that's a plus 5 at the end, never mind. I thought that was the minus 5.
Can't be
It's
5
not
or
gonna be
negative 5.
0.
C can be any real number.
Yep.
You can't take a real number, plug it in here, get it squared, and end up with negative 5. So
Oh,
your
that's
denominator
true.
can't be 0.
Yeah.
Okay, let's look at this one.
That's your answer. That's all you have to do.
That's your answer. That's all you have to do. Sometimes. Sometimes they're a little bit trickier, like what we were doing over there when we had that x minus 1 in the denominator.
Once we
But a lot of the times, it's just as simple as just plugging in the numbers.
Okay.
Yeah, nice and simple. All right, let's look at this one.
Okay.
Limit as x approaches 2, what is it?
So 4 times 2 squared minus 3 rooted.
So what is it?
Square root of 13.
Square root of 13, right?
Yep.
Plug in 2 for x. 2 times 2 is 4.
8,
4 times 4 is,
16.
there we go, minus 3 is,
Okay.
take the square root.
Cool.
Easy, easy. Okay, so like you just barely stated there, but we'll state it again. If p of x is just some polynomial expression, then the limit as x approaches c of p of x is just p of c. So if your expression is just a bunch of constant times x to some power plus constant times x to some power, like this, some polynomial expression, you can just replace all the x's with c's and you're done. Like what we did in the numerator here, what we did up here. Make sense?
Yep.
So if it's just simple polynomial expression, you can just plug in the c. Second, if p of x and q of x are polynomials, and q of c, the denominator at that point, is not equal to 0, then the limit as x approaches c of their quotient is just plug in the point. So as long as your denominator is not 0, like it wasn't 0 here, you can just throw it in. When it is 0, a little bit harder. But when it's not 0, just plug in the point. So, pretty much anytime it works to just plug in the number, just plug in the number.
So if if x is approaching c, so then you plug in c, and then you're saying c, if c is a denominator and it's, you know,
C is not the denominator. Q of c. If Q of c is not equal to 0, you're good.
What I'm saying is if it is equal to 0,
Like what we had over here.
which what we're saying is that it's getting near 0, technically.
The denominator, as x approaches 1, the denominator gets arbitrarily close to 0.
So by plugging in though,
But if we were to just plug in, then we would get 0, which is bad. Can't divide by 0.
but we're near 0, technically. Is
Right,
that
but what
saying?
we're saying is the limit is oftentimes just the value of some other expression. The limit of this thing at 1, turned out to be the value of this thing at 1. The limit of this thing near 1 is the value of this thing at 1. So if we want to change it into something we can't take the limit of. Most of the times, just plug in the number and it's the same thing. Because that means your function is just behaving nicely. If I've just got some nicely behaving function like this, and I say, what's the limit? So here's my x-axis, here's my x1. If I say, what's the limit of this function at x1? It's just f of x1. The functions are behaving nicely there. Nothing weird's going on. The limit and the value are the same thing. So when the limit and the value are the same thing, when your function's behaving nicely, is basically what these are saying, when you have nice functions, then don't make it hard for yourself. Just plug in the point.
Okay.
Which is essentially when you're counseling at the top and the bottom.
No, that's when you have something bad, and then you need to make it behave nicely. So we'll do some behaving bad ones, but let's do these real quick.
Go ahead.
So let's look at the limit as x approaches -1 of this expression. Plug -1 to the denominator, what do we get? 2, right? So, doesn't go to 0, so we can just plug -1 in. This is a nice behaving function. So this is equal to -1 cubed plus 4 times -1 squared minus 3 all over -1 squared plus 1. which is equal to what?
Negative 1 plus
0.
Follow that? Negative 1 plus 4 minus 3 is 0. Denominator, who cares? The numerator is 0, the whole thing is 0, as long as the denominator is not 0, which wasn't.
Okay.
Good?
Yeah.
Okay, now let's try this one. If we plug in 1, what's the denominator?
0.
Ah, shoot. So it doesn't work. So now we got to get tricky with it. And we got to rewrite the expression. And when in doubt, factor it out, right? So how can we factor the numerator?
It's
Anyone but Emma.
okay.
The x squared.
Holy camoli. You guys don't know how to factor that? Okay, it's going to be an x and an x. We need two numbers here that when multiplied together give you negative 2, but when added together give you 1, because the coefficient of just x is 1. Two numbers that multiplied together give you negative 2, but added together give you positive 1.
Positive 2 and a minus 1.
Positive 2 minus 1. Thank you. Let's work backwards to make sure this works. X times x, that's x squared. 2 times x, that's plus 2x. Negative 1 times x, that's minus x. Negative 1 times 2, that's minus 2, is equal to x squared plus x minus 2. Crazy, it worked. All right. You guys should have done a lot of these problems before. I need to give you a whole sheet of just factor this. Okay. Let's see if you can factor the denominator. Not Emma.
X minus 1, x plus 1.
Oh, I was so happy for a second. What can I pull out of both those terms?
X.
X, what does that leave me with?
X minus 1.
X minus 1. Okay.
Got half of it.
You got half of it. Anyways, what do we notice?
You can cancel out the x.
X minus 1 on the top, x minus 1 on the denominator, those cancel out. We're left with the limit as x approaches 1 of x plus 2 over x. Okay, now what about that thing?
It'll work.
X cancels.
It works. So tell me what's all equal to?
3.
There we go. 3. Calculate the limit.
How does that work if the x? Oh, I meant right.
All right. Well, this next one's going to be fun.
Yep.
Let's get started. What's the limit as x approaches 0? Uh-oh. Denominator is broken, right?
Yep.
Okay. So, what do we do now?
You try to factor.
We got to try to factor. Uh-oh. Can't really factor.
Root.
Now what do you do? Well, if you can't
It's
factor,
simplified, right?
that's already pretty simplified.
No, I'm
If
saying
you-
you can get rid of that root, can you not?
Entirely.
This thing?
Yeah.
I don't think
X
you
and
can
a
do
denominator.
No. There's nothing you can do with that square root. A sum of squares does not factor. Discrete math 101.
Mm-hmm. Why not?
You can't, if I have x squared plus y squared, I can't factor that in any way.
Yeah. But you have your.
That's something squared plus something squared. I can't factor it, so I can't take its square root.
You can't.
Because it's not something times itself. This, okay, let's make something very clear. This is not equal to x plus y.
So we're not allowed to plug in 0.
Yeah, you can't plug in 0 because the denominator goes to 0. And you can't take the square root of that
But
because that's very different.
isn't that equal to root x2 and then plus another root of 10? I mean, 100.
This thing?
Why doesn't it work?
I don't know what you're saying.
Why doesn't the 100 turn into a 10?
So what? Tell me what I'm writing.
X squared in the root.
X squared right
And
here.
then another plus outside of it.
So you want to do plus.
And then root 100. isn't that equal to?
That's exactly what I was saying right here.
You can't do that.
You cannot do that because square root of x squared does the same thing as x plus 10.
Now, if it's
This goes to this, but this does not go to this. This and this are very different things.
down, down.
Not close to the same thing. Here's how I can show you it's not close to the same thing. Let's look at the square root of 9. What's that equal to?
3.
3. But now let's look at the square root of 1 plus 1 plus 1 plus 1, 6, 7, 8, 9. Okay,
4.
that's the same thing, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's break that up into their individual square roots.
Yeah.
Okay, now that's the square root of 1 plus the square root of 1 plus the square root of 1. But that would just come out to, if we did what you said, so if I did square root of 1 plus dot dot dot, did that 9 times, that would be equal to 1 plus dot 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 9 times, which is equal to 9. The square root of 1 is just 1.
Yeah.
So if I break that up into 9 square roots of 1, then that turns into 9 ones. Add those up, that's 9.
Okay.
So no, you can, this to this is fine. This to this, no. The square root of a sum is not the same thing as the sum of a square root. So this is not equal to make it very explicit, x squared plus y squared.
So you can only do it if there's one term.
Yeah,
You can break up the
you can do products. Anyways, so no, you can't just do that. Okay. So this expression does not simplify. We can't factor it. Now what do we do? What do we do when we have weird expressions that we can't factor, can't see how to simplify? There's another trick that we commonly use.
Called on me.
Multiply by 1.
Multiply by 1. Maybe we can multiply this by some 1 that changes it in a way that's useful, makes out we can see something. So we're going to multiply. This is equal to, I'm going to drop the limit for a second. So maybe I'll just do an arrow here and we'll do the expression. So I'm going to take square root of x squared plus 100 minus 10 over x squared. And I'm going to multiply it top and bottom by plus 10. Now, where on earth did I pull that weird, oops, that's not 1. Top and bottom, same thing top and bottom. Alright, so I'm going to multiply it by 1. You with me there?
Mm-hmm.
Multiply it by 1. Why did I pick this special one where it's the same thing here but flip the sign? Turns out when you're multiplying a square root by a 1, this is how you typically want to do it, and it just comes out prettier. There could have been 101 different ways I could have solved this problem. This would have just been a common approach. There's a good chance that Emma was thinking of this exact same thing, in other words. We didn't just pull a random number out of a hat. So this same expression, just change the sign, because it's going to get rid of the radical in the numerator when you do the algebra. So we'll multiply it out and you'll see why that made the numerator nice, even though it made the denominator ugly. So that's equal to, this times this is equal to x squared plus 100, right? It's no longer a square root because we had 2 of them. So the square root times the square root just gives me a term. Then we have, let's do this times negative 10. That gives me minus 10 of those square roots. Right? Now, so I did this times that, I did this times that. Now let's do this times that. That gives me plus 10 of those square roots. And then finally, negative 10 times 10 gives me minus 100. Follow all the algebra there?
Yeah.
And notice, negative 10 and 10, those go out. So your radicals go out. So it makes the numerator nice. That's why we picked the plus sign. Just keeps the numerator nice. All right, and now this is all over x squared times the square root of x squared plus 100 plus 10. Oh, we need parentheses. Yep. Good? So now, simplifying, we are looking for the limit as x approaches 0 of, let's see what we have here, of x squared plus 100 minus 100. You with me on that? Are you okay with me just getting rid of those hundreds?
Yes.
Okay. So I'm just, see how the numerator just goes straight to x squared.
Yeah, but you wrote the limit of x going to
What the?
8 or
I don't even
something.
know what that was. It's like I wrote a degree symbol there. Okay, my numerator is x squared. My denominator now is x squared times the square root of x squared plus 100 plus 10.
Okay.
Now what can I do?
Just get rid of
Cancel it out.
Cancel it out, so that leaves a 0 in the numerator, right? No, it leaves a 1 in the numerator.
Yeah, one.
1, so this is equal to the limit as x approaches 0 of 1 over the square root of x squared plus 100 plus 10. Now notice that from the beginning, what was giving us a problem?
The 0.
The x squared is in the denominator though,
Yeah.
right? Because that kept going to 0. Notice now, we got rid of that pesky term.
It can't be 0.
Yeah.
So now, when we plug in 0, what do we get?
20.
1 over
No.
20.
1 over 20,
Yeah.
right? That's its limit.
Yeah.
Now the author has a discussion in the book about how if you plug numbers into this thing doesn't behave nicely. And so if you were to start plugging numbers into it and see what it gets closer and closer to, then you actually might come away with the conclusion that it gets closer and closer to 0 and not 1/20th. Because this function kind of, for what we call typically small numbers, it actually gets closer and closer to 0, but for really, really, really small numbers, it suddenly goes down to 1/20th.
It's so weird.
So you got to be careful with just plugging in points to figure out these problems. You need to actually calculate them. If you just plug in points, you might have walked away with the conclusion, oh, this gets closer and closer to 0.
So, if, let's say, you can't times it by 1, or you times it by 1 and you're still not able to break it down, is it just simply something you can't solve using this limit method?
It's very possible that you can't calculate the limit of things. Typically, all the problems that you're given where you're told to calculate the limit, you can calculate the limit. So they're like already making sure they're giving you good problems. And you always have the answer in the back to check for sure that you can. Make sense?
It does.
Okay. And we're not going to cover all that. Looking over at the side whiteboard now. We'll ignore this. This is just in case we got ahead. We're going to look at what's called the squeeze limit, or the squeeze theorem. So suppose that g of x, f of x, and h of x, so we have three functions. We have these three functions such that f of x is sandwiched between g of x and h of x. Okay?
Okay.
So I'll suppose that we have these functions where f of x is sandwiched between these two other functions for all x in some open interval containing some point c, except maybe at the point c itself. So maybe it misbehaves just at the point c, but everywhere else on the interval, this is the case. Right? We're going to be talking about a limit, so we don't care what happens exactly at c, but all around c, this is the case. With me so far?
Yep.
So what does our picture look like? It looks roughly like this. G of x is down here, f of x is sandwiched in between them, h of x is like this on some interval. What happens exactly at the point C? Who cares? But everywhere else, here's what it looks like.
So that should be like a circle.
It could be circle, it could be filled in, who cares? It could be anything.
Oh.
Doesn't matter. So ignoring the point C itself, all the other points behave this way. And suppose that the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x. So in other words, g of x and h of x, the bottom of f of x and the top of f of x, both get closer and closer to the exact same point.
Okay.
If they do, then f of x, the thing between them, also gets closer and closer to the exact same point.
Okay.
Make pretty good sense?
Yeah.
Right? So if the top function gets closer and closer to 1, and the bottom function gets closer and closer to 1, the function sandwiched in between them has to get closer and closer to 1. Because it's always between them.
Okay.
Make sense?
Mm-hmm.
So let's show some things really quick. I need this chair. Maybe what we'll do for the rest of the day, maybe I'll keep going with this material. Give you a little bit of insight tomorrow, answer questions, and we'll start the test tomorrow. So we'll do tests first thing tomorrow morning, rather than at the end of class today. Does that work for everyone?
Yeah.
Because I want to make sure you have at least an hour, and we're kind of pushing on time now.
Okay.
Okay. So, maybe here's what we'll do then. Maybe we'll do break real quick, take 10 minutes, and then we'll come back, we'll cover this material, then we'll go over any of your questions. How's that sound?
Sounds good to me.
Good? All right, let's do that.
Okay.
So let's do break. Keeping up?
I'm trying to.
It's a lot.
Yeah.
But now you'll be set when you get to college.
Sophie told me to tell you that science board doesn't want to count physics as a science class.
Oh my wow, who's the science board?
Bob Brigham, Mr. Zitting, Mr. Steed, somebody else, Caroline, I think it was.
Someone is pushing an agenda somewhere.
What did they say?
They decided that it was too math-based, so it's an upper elective instead.
So I have to take
So we still have to take another science.
You'll need a science, is what they're saying.
Yeah.
But that is an absolute joke.
Yeah.
So I don't know if that matters for any of the seniors.
Probably not.
If this comes back to bite you for next schedule, next year, come find me.
It just means I'll have to take a junior class.
Not necessarily.
Well, that's the only sciences they offer. It's senior junior classes. So I'd have to take anatomy next year.
It switches up year by year.
So
It's not the same stuff every year. But yeah, if I were you, I'd take physics next year. Because
yeah.
especially since they're not going to count it. They count what you're doing now as a science. Because Brigham, he actually knows this stuff quite well. And physics is one of those things where you could go over it 3 times and still not get it all. I mean, it is. There's just a lot of fun, cool concepts. And if you did it once, where with me, where we're going through all the math, and then you went and did it again, where now you were just focused more on the concepts, I think you'd have a ton of fun. Also, programming. I don't know if that's junior level, but who cares? My brother Garrett's programming class. That'd be a great one for you.
Yeah. That'd be fun, but that's not an elective science.
There is a
Not
upper elective
upper
science.
science, advanced science.
Advanced science.
So the advanced sciences is anatomy, chemistry, environmental science, and physics. That's all they offer.
They don't like count computer science. That's weird.
Otherwise, that'd be really fun.
Computer science would be a ton of fun.
But they're just like, if we need science next year, which won't be too bad.
Now, if that turns into a problem, I'm happy to get involved.
Sophie says it wasn't going to, so she doesn't want you to look mad at her.
No, but I can talk to whoever. It makes 0 sense.
I know.
And anyone who understands knows it makes 0 sense. Like, there's no way that Brigham, knowing what I would do, would say, no, we can't count that as a science. There's no way Tyler, knowing what I'm doing, would say, no, we can't count that as a science. Like, I'm positive that they wouldn't think that. Because it makes no sense. So someone's pushing an agenda somewhere. Because they're just mad.
That's all
Yeah. So it makes zero sense. So yeah, I'll push for whatever you need.
Cool. We'll see next year what needs to be.
Yeah, that's a go.
Good. We'll go with your dreams. When did you want us back?
7 minutes.
Okay.
Is there a lot of times where it's appropriate to use the term infinity instead of undefined?
Use the term what?
Infinity instead of undefined?
Well, infinity isn't a real number.
I understand that.
So you can't say that a product of two real numbers gives you infinity.
You could say infinity divided by infinity equals 1 though, right?
No, it depends on your infinities. That's the problem. So we will deal with a lot of concepts like this. So let me give you one that will probably go down what the vein you're after.
Yeah.
Let's look at the limit as x approaches 0 of 1 over x. Now this we would say it tends towards infinity.
Yes.
Yes.
Right. So, not only that, but you told me that undefined doesn't work because it could be any number. But what if you have undefined, which is divided by NB, is always going to be equal to 1, even though it's not
No.
because you said any number you want.
That's not a number. Undefined isn't a number. It's not even a definition.
Why is it not a number?
Why is something undefined not a number?
What I'm saying is,
A number
whatever
is
you
a
want.
set of things that follow certain rules and properties.
I understand.
Undefined means we're talking about something that doesn't have a definition.
Well, okay. I'm talking about the source. Why would we call something undefined? We just call it undefined. It's
We
not
called it
necessarily is undefined.
So, give you an example. If I'm going to say 1 divided by 0 equals something, you have to say it equals something. What do you want to equal?
Yeah, right. What do
Let's say it equals x.
Sure.
That means 1 is equal to x times 0. So find the thing that makes that true. Well, nothing works, because we have a theorem of the basic axioms of arithmetic that 0 times anything is 0.
I see what you're saying. No, I'm glad you pointed that out.
So it doesn't work. It's not that someone arbitrarily said, no, we're just not going to work with this thing. It's provable that you can't give it anything.
Well, what's kind of bothersome to me here is that if this limit makes this 2, technically that's not true because the limit will, for infinity, be 2 point something that is.
We're not talking about the value of a function at that point. We're talking about what is it getting arbitrarily close to. The value it's getting arbitrarily close to is 2. There is no other number you can plug in there that's getting arbitrarily close to.
Yeah, but that works so well when technically. I don't know.
We're not coming at calculus rigorously, so I can't prove these things to you. But the same way that you would want this to be some number other than 2, it's kind of like saying, give me the number just bigger than 0. Give me the number just bigger than 0. You can't. It doesn't matter what number you pick. Pick any number bigger than 0, epsilon. Epsilon bigger than 0. Typically we use epsilon to represent a really small number. Doesn't matter how small of a number you pick, you can't find the number just bigger than 0. Because however small of a number you pick, 0, epsilon has, will always be in between epsilon and epsilon. This number is always between those two.
Yeah, right.
So you have to, you can't talk about the other number closest to 0.
Gotcha.
So this is saying, what's the number arbitrarily close, what is this getting arbitrarily close to?
Okay, but when you get the end result, you have this 2 value, which now you can use effectively in whatever form you want. But in a way, it's sort of lost its where close to 2 because you don't mention that. Isn't that a problem? Like it seems like it's equal to the limit of x.
The limit as x approaches 1, well, come back to the initial expression. The limit as x approaches 1 of this expression gets arbitrarily close to 2. What do we mean by that? We mean pick any number close to 2 that you want, but not quite 2. I can make this expression give me that number. You can pick 2.00001, fine. I can find the number in the domain that spits out 2.00001. Pick any number as close to 2 as you want. I can always make that come out. That's what we mean by arbitrarily close.
But didn't it kind of lose it when she says equals to this 2?
No, I didn't say that. I never said that this function is equal to 2 at 1. I said the limit as x approaches 1 of the whole function is what it is.
Yeah.
A limit is a different idea than just an expression saying equals. We are not saying that f of 1 is equal to 2. That's definitely not the case. We can't say that. It's a whole different idea. The limit as x approaches 1 of f of x is equal to 2 is what we're saying. We're saying that the function gets arbitrarily close to 2. Maybe it actually gets there, maybe not. It gets arbitrarily close to 2. That's what it says.
Yeah, that makes sense.
And to get rigorously what it says is a real analysis class, not a calculus class. Although we'll get some rigor here in a sec.
Cool. Good, thanks. Sure smells good though.
Never had bacon flavored chips before.
Pringles, I don't actually know what Pringles.
They're so good.
It tastes like something with a bunch of mush, and they just fried it in a chip shape. So when you put it in your mouth, it just turns back into the mush.
Yep.
They're pretty good. It's good mush stuff.
Well, a lot of people like it. To each their own.
Oh no, I just love texture more. I like Doritos more though.
Other than psychiatric care, they turn a president or French president, or whatever it's called. Okay.
All right, let's continue.
There.
Okay, so we just really talked about this, I don't know what they call it, squeeze theorem or sandwich theorem or something like that. But you got the idea. If our function is sandwiched in between two other functions, and those two other functions, their limits approach a particular value at a point, namely L, then the sandwich function also has to approach that same value. Picture looks roughly like this. Make sense?
Mm-hmm.
All right, let's use an example. So let's look at cone functions. So we'll look at this function, and then some function we don't know anything about. So given that 1 minus x squared over 4 is less than or equal to some mystery function, is less than or equal to 1 plus x squared over 4, for all x not equal to 0, find the limit as x approaches 0 of our mystery function.
Okay.
You understand what we're trying to do?
Yep.
Okay. Well, let's look at the limit as x approaches 0 of this expression. What is it?
1.
1. Everyone see how she's getting 1?
Yep.
And what about for this expression?
Similarly, 1.
1. Therefore, we know that this is equal to 1.
Okay.
Pretty straightforward.
Pretty straightforward. Sandwiched between two of them. So let's look at another example. Let's look at the limit of sine of x, right over here, so that hopefully you can see better. Let's look at the limit of sine of x as x approaches 0. And see what this equals. Now, you might remember from last week, just close to the end of class, I think, one of the last things we showed is that negative absolute value of x is always less than or equal to sine of x is always less than or equal to absolute value of x.
Yep.
Remember that inequality?
Mm-hmm.
Okay, so what's the limit then as x approaches 0 of negative absolute value of x?
0.
It's just 0, right?
Yeah.
What's the limit as x approaches 0 of absolute value of x?
0.
Also
0. So sine of x is sandwiched in between these two things. The limit of these two things goes to 0. Therefore, sine of x has to go to 0.
Okay.
All right, now let's look at cosine of x. And similar thinking, so we want to see what the limit as x approaches 0 of cosine of x is. Now, what was our inequality for x? Do you remember? It's negative absolute value of x is less than or equal to 1 minus cosine of x is less than or equal to, sorry, that's a less than or equal to absolute value of x. I think that was it.
Yeah.
Okay. Once again, we know that this thing right here, well, let's do some algebra, maybe. How do I want to do this? Well, we'll still be fine, I think. So the limit of this thing is what? As x approaches 0, what's the limit of this thing?
0.
So the limit of this thing is?
0.
So the limit of this whole thing has to be 0. So I know that the limit as x approaches 0 of the whole expression, 1 minus cosine of x, is equal to 0. With me?
Yeah.
Using some of our rules that we have written over there for limits, I can rewrite this as the limit as x approaches 1, or the limit as x approaches 0 of 1 minus the limit as x approaches 0 of cosine of x, I don't know why I'm doing parentheses like that, is equal to 0. You with me there? Move this to the other side, but now I'm going to write it first. So the limit as x approaches 0 of cosine of x is equal to the limit as x approaches 0 of 1, which is equal to 1.
Okay.
You follow that? Now hopefully these two were intuitive, because think about your unit circle. What is your x coordinate at 0? 1.
1. Sorry.
What is your y coordinate at 0?
0.
0.
Okay.
So the functions are already behaving nicely around those points, and so it's not a surprise that the limit as x approaches 0 of sine of x is the same thing as just sine of 0. And the limit as x approaches 0 of cosine of x is the same thing as just cosine of 0. So those shouldn't be very surprising results. Make sense?
Yep.
Okay? And then I think I have another problem right here. And that if, all right, let's see what this is saying. What am I showing now? So I showed that the limit as x approaches 0 sine of x is equal to 0. I showed that the limit as x approaches 0 cosine of x is equal to 1. And now show that if the limit as x approaches 0 of the absolute value of f of x is equal to 0, then, well, I think that's supposed to be c now. So we're not using 0 anymore, saying any point. If I take the limit as x approaches some number of the absolute value of a function, if that goes to 0, then the limit of the function at that point goes to 0. That's what we're going to prove now.
Okay.
You with me on that? Okay? Good?
Yeah.
Okay. So, the one thing to note maybe, let's note it over here, is that negative absolute value of a is always less than or equal to a is always less than or equal to absolute value of a. This is always the case. Pick any number. 2. The negative absolute value of 2 is less than or equal to 2 is less than or equal to the absolute value of 2. Pick another number. Negative 3. Negative absolute value of negative 3, or in other words, negative 3, is less than or equal to negative 3 is less than or equal to absolute value of negative 3, or 3. Make sense? So, notice that this is always the case. Negative absolute value of f of x is always less than or equal to f of x is always less than or equal to absolute value of f of x. You with me?
Say always less than, but
Less than or equal to.
I
It can
guess
be equal.
0 would be an exception.
Now, pick the number 3. Plug it in here. Negative absolute value of 3 is less than or equal to 3 is less than or equal to absolute value of 3.
But negative 3 is always going to be.
So we get negative 3 is less than or equal to 3 is less than or equal to 3. Notice that those are equal.
Yes.
So it was equal in that case
Yes.
on this side. Now let's instead replace it with negative 3, negative 3, negative 3. This comes out negative 3, that's negative 3, that's 3. Now it's equal on this side. So you always need less than or equal on both sides. Okay. Now, okay, so we got it sandwiched like we wanted, and now we're basically done, right? Because now, what's the limit of this thing? 0. And now we just have negative 1 times 0 is negative 1. Remember our limit rules. This can be reviewed as just negative 1 times this whole thing, right? That's the same thing.
Yep.
And so the limit of this whole thing is the same thing as the limit of this times that. You can pull constants out of limits. You with me? So we know that this is then negative 1 times 0 is less than or equal to the limit as x approaches c of f of x, which is less than or equal to the limit of this thing we already know is 0. So this has to be 0.
Okay.
Make sense?
Yep.
Okay. So now let's show those three things. Theorem 5. If f of x is less than or equal to g of x for all x in some interval containing c, except possibly at c itself, remember we don't care what happens exactly at that point, we just care about around the point. And if the limit of f and g as x approaches c exist, then their limits are less than or equal to each other. Okay, so this one's pretty intuitive. Look, if this thing is always less than or equal to this thing, around some point c, then their limits have to be less than or equal to each other at c.
Okay.
Pretty intuitive?
Mm-hmm.
Okay, so that finishes up the chapter. Not the chapter, section. That finishes up 2.2. So now we're done with 2.2. Moving on now to 2.3. We won't cover 2.3 today. I'm just going to introduce it to you, and then we'll let it stew. Because now we're going to talk about probably the densest definition you're going to deal with in this whole class. And so it's going to be a lot to soak in. So we're going to give it to you now, and then we're going to come back and attack it first thing tomorrow.
Well, aren't we doing the test first thing tomorrow?
Yeah, after the test. Okay, so here's the definition. There's a lot going on. Pay close attention, because you're coming up to the hardest part of probably the whole class, and the hardest problem you're going to have to solve is using this definition. Okay, so let f of x be defined on an open interval about some point c, except possibly at c itself. So we've got some open interval around some point c. So here's c, we're talking about some interval around that point. That's all we're talking about so far. Good?
Yep.
We say that the limit of f of x, the limit of the function, as x approaches c is the number L. So looking at our picture, here's c, L is here, here's our function f. And we're defining now what exactly it means to be a limit. So far we've just been saying it, and now you get it, kind of, we give you the gist of it, you get the general gist of what's going on. We're coming up with the definition now. It's called the epsilon delta definition for a limit.
Okay.
So we're going to give a definition to exactly what the scene has been talking about the whole time. So here's what we're saying. So look at some open interval around a point c. We say that the limit as x approaches c, so x is somewhere in this interval getting closer and closer to c, not quite c. The limit of the function as x approaches c is equal to L. And we write the limit as x approaches c of f of x is equal to L. So we say it and we write it like this. Provided that what? What does it mean for the limit to be L? It means that for every positive number, every epsilon greater than 0, epsilon is just a stand-in for us. We typically use it to represent variables for small positive numbers. But for every positive number epsilon, there exists a corresponding delta that's a positive number, such that for all x in the interval, if x is within delta of c, then f of x is within epsilon of L.
Can you explain that?
Yeah, I can. Hopefully. It's a hard one. So let's read it again. For every epsilon, epsilon is going to be some distance around L. So for every distance, for every interval you make around L, so epsilon's this distance right here in my picture. You with me?
Mm-hmm.
So pick whatever small positive number you want and make it that kind of interval around L. So provided that for every epsilon around L, there exists a corresponding delta. Sorry, I didn't write my deltas down here. So here's C. This is C plus delta, and this is C minus delta. Okay. There exists a corresponding delta around C such that anytime you pick an x within delta of C, so anytime we pick an x in this interval, then its corresponding value, f of x, is in this interval.
Okay, that makes sense.
Okay.
It's kind of like topology.
Oh, true. You did topology. You deal with a lot of dense abstractions there, but
Yeah.
for people that haven't dealt with this notation before, this is going to be a mouthful. It's a lot to take in one go. So let's go over it again. What does it mean? So we say that the limit of f of x as x approaches C is equal to L, provided that for any epsilon you pick around L, I can find a corresponding delta around C such that all the points within delta of C map to points within epsilon of L. Make sense? Let me change my picture here to help bring the point home. Let's pick a smaller delta really quick. I should have done this to begin with, and I think it'll help more. So, pick a smaller delta in my picture. So here's C plus delta, and then over here is C minus delta. You with me? Now, notice that if we look at the image of all these points, drawing up a pointed line, it goes up to like right there. And draw up a dotted line, it goes up to like right there. So all the values of the function on this interval is this interval, right? Which is inside this interval. That's what we're saying. We're saying if for any interval I pick around L, you can find a small enough interval around C so that all the points in that interval map inside the initial interval, then it's it is the limit. Go ahead.
Can the delta be exactly what the epsilon is, like the interval?
Yeah, it can be equal to. It's just what these map to have to be a subset of this. Typically, it's easiest when you're actually solving these to just make it equal. But it doesn't have to be equal. Okay. So, say that again. For every epsilon, there exists a delta, such that if x is within delta of C, then f of x is within epsilon of L. That's what this is saying. So I'll read it again. If for all x, remember that the absolute value between 2 points gives you their distance, right? So the distance between x and C is less than delta, implies the distance between f of x and L is less than epsilon. See how to read that? For those of you who did logic and want the dense notation, here it is. If for every epsilon there exists a delta such that x being within delta of C implies that f of x is within epsilon of L. This is logically equivalent to, this says the exact same thing as the limit as x approaches C of f of x is equal to L. It's a definition. What does this mean? It means this.
What exactly does epsilon mean?
It's just a small positive number.
Okay.
It's a variable. Well, it's not a variable because it's given to you, but yeah, it's just a number. It's just a positive number.
So just a number.
It's just a convention to use epsilon in this case the same way that we typically use x1 for an x coordinate. I didn't have to use x1, so if I said look at the point x1, y1, it's typical that I call this coordinate x1, that one y1. There's no reason I have to do that, it's just convention. Similarly, it's convention to call this distance epsilon and this distance delta. It's just a positive number. Some number greater than 0. That's all delta is. And that's all epsilon is. Epsilon some number greater than 0. Delta some number greater than 0.
We use the term delta, but that doesn't now apply to delta over here.
Oh, sorry. Greek letters. This is a lowercase delta. This is an uppercase delta. So we're using the lowercase delta.
And okay, lowercase delta, but they're the same word, sound, but different, completely different meaning.
Yeah.
Gotcha.
Delta, now we're just talking about the variable rather than a change in something. Good point. Okay. Now, in case anything was lost in translation in that picture over there, I want to make something very explicit. If the distance between f of x and L is less than epsilon, that is the same thing as f of x is in the open interval from L minus epsilon to L plus epsilon. Those say the same thing. Maybe a better way to have written this would have been, this right here is equal to, let's write it this way because I think this will help a lot. Negative epsilon is less than f of x minus L is less than epsilon. Right? Going from here to here, if you want to get rid of the absolute value, you just need to make sure that you handle the negative on this end. Because if it comes out positive, it's definitely less than this. Now if it comes out negative, it can't be more negative than negative epsilon. So that value is always sandwiched between those two numbers. With me so far?
Yeah.
Okay, now it's just a little bit of algebra. I'm going to add L to all 3 points. So now we get L minus epsilon is less than f of x is less than L plus epsilon. With me? So f of x is somewhere between L minus epsilon and L plus epsilon. Which is exactly what we meant here. F of x is in the open interval, L minus epsilon to L plus epsilon. Or f of x is somewhere in here. So in this case, if we drew the dotted line back, f of x is right here. You with me?
Makes sense to me.
All right. It's dense. Maybe if you went and watched some videos of other people explain this definition, that would help. Maybe go reread the definition yourself. I don't know. We'll re-go over this definition first thing tomorrow after the test. But this is the hardest definition to wrap your head around in this class, by far.
What's this arrow line? What does that mean exactly?
Sorry.
The line
This.
with 2 arrows.
Logically equivalent
No.
to.
Oh, that?
Yeah.
They're logically equivalent. They say the same thing. This says the same thing as that, and that says the same thing as that.
Logically equivalent, kind of like an equal sign for an equation.
Kind of. Equal signs for an equation says that they're identical, not logically equivalent.
I know. Okay.
Yeah. The difference would be thinking programming wise. The way we use equal in math, it's like 2 things are the exact same object, not just they have the same properties. This is more like they have the same properties. Not they're actually the exact same pointer to the exact same object.
Okay, that makes more sense.
Okay. So let's look at a bad picture now to help make this definition make sense. So this picture was helping us make sense of the definition. Let's look at a point where the definition doesn't work and see how it violates the definition. You with me? So let's look at a bad picture. So here's a function. It goes up, includes that point, stops, jumps up here, and continues on its merry way. Weird function, right? Obviously behaving very badly at C. And so if I ask you what's the limit of this function as it approaches C, the answer is, I can't do it. What is it getting closer and closer to? Is it getting closer and closer to this number, or is it getting closer and closer to this number? I'm saying let's do something bad, and let's say, I think it's getting closer and closer to this number. This is a bad scenario. I'm setting up a bad case. Right? So I'm saying let's try and say that the limit is actually this value right here, L. And let's see how this breaks our definition. You with me?
Yep.
So we know intuitively that this shouldn't work, and this should somehow break our definition. So I'm trying to make you see how the definition is broken in this case now. Good? Okay. So let's look at our function. Here it is. Maybe you want some actual numbers. Should we do some actual numbers here?
I think that would be helpful.
Okay. let's do some actual numbers. So I'll redraw a picture. I'll pick a function really quick that behaves badly and then draw the picture. So let's pick a function something like f of x is equal to, we'll do x for x less than or equal to 1, and then we'll do 5 for x greater than 1. With me? So it's going to have that weird jump in it. It's definitely going to have a point where we can't calculate the limit. So this. Kind of went high. Should stop better. All right, one more time. Okay, drawing our picture. Here's our function. Goes like that. And then here we jump up to 5, and then we continue on our merry way. Right?
Yeah.
So now let's show that the function, we are showing that this is a bad statement to make. You cannot say that the limit as x approaches 1 of f of x is equal to 1. Bad statement. No, that is not the case. And we're going to show that that's false using our definition.
Okay.
All right, so how does this work? I need to find an epsilon around the point 1, since you're claiming it's 1, so you come to me and you say, the limit's 1. I need to prove you're wrong. So I need to find an epsilon around that point, such that no matter how small of a delta you pick around C, we shouldn't have picked one where L and C are the same thing. I'm going to switch this up to x plus 1, just so that our input and output aren't the same thing. You with me?
Mm-hmm.
Try and keep it less confusing. So now the function looks like that. Right? So now you tell me that the limit as x approaches 1 is 2. Okay. With me? So I say, okay, I'm going to pick some interval around this point 2. I'm going to let my epsilon equal 1. So we're looking at this whole interval now from here to here. Here's the interval we're looking at, right?
Okay.
So now your job, if you're going to say, actually I'm right, you need to pick an interval around the point 1 here. You need to pick some interval small enough such that all the points in that interval map into my interval.
Okay.
You with me?
Mm-hmm.
So pick some really small number.
Just
Let's say you pick a really small number, whatever it is. So here's 1. Let's say you pick a really small interval, so it's just that teeny interval like that. You with me?
mm-hmm.
Well, let's look at the image of all those points. The image of this maps up to here, which maps out right there. So that one's still good. But look at this one. This maps up to here, which is right there, which is way outside the little interval I chose. So it doesn't work. The only way it's continuous at that point is if for any interval I pick around here, you can always find a little interval around here, such that it maps all those points inside my interval. That's the only way you can say that the limit is that value at that point. Sorry, I keep saying continuous at that point because it's basically the same thing. So, sorry, the limit. The limit at that point is only that value if this is always the case. If for any interval I pick around what you're calling the limit, you can always find a delta around a point such that all those points map inside the interval I chose. So let's read the definition one more time, and then hopefully with these two examples, it will start clicking. When is it true? So, let f of x be defined on an open interval about C. We say that the limit of f of x as x approaches C is the number L, provided that for every epsilon greater than 0, there exists a corresponding delta greater than 0, such that for all x, if x is within delta of C, then f of x is within epsilon of L. Or, for every epsilon, for every positive number, there exists delta, some other positive number, such that if x is within delta of C, then f of x is within epsilon of L. If that is the case, then yes, the limit as x approaches C of f of x is L. But only if that's the case. Otherwise, it's not the case. Does it feel like it's starting to sink in?
A little bit. I'm having a hard time determining why it matters that you have to come in from both sides.
The interval here just has to always map into this thing.
What I'm saying is, why is it? Oh.
And yeah, from topology, you'll notice that
Yep.
this was the definition we used for a continuous function, but we have a much better definition for a continuous function in topology. What is it?
A continuous function in topology?
Yeah, what's the definition of continuous function in topology?
I don't remember.
What is it, Emma?
Something to do with topological spaces, maybe?
No.
A function is is continuous if the pre-image of open
Is
sets
continuous.
Is open.
are open. You
Open,
can't
sorry,
use the
are
word
open.
in this definition. All right. Anyways, that's what we're covering for today. We'll call it there. We'll go over any problems you have, and then, does this need to be recorded?
Clarification. The L variable is what they're claiming the 2 is, right?
Yes.
Okay.
Yes.
So
But they're claiming the limit as x approaches c is L, the limit.
the intervals have to be equidistant
Nope.
from the center.
It's just easiest to work with equidistant ones.
So
Look, the problem is, on this function, no matter how teeny tiny an interval you include over here, ignore the left-hand side. Here's one. You have to have an open interval. So you have to have some points, you have to include some point to the right of 1.
what exactly does an open interval mean?
Open interval. 0 to 1 is an open interval. It's all the points between 0 and 1, not including 0, not including 1.
Sounds like a closed. Oh, okay.
That's an open interval.
Okay, what's not an open interval?
Here's a closed interval. 0 to 1. That's all the points between 0 and 1, including 0 and including 1.
Okay.
So you cannot construct an open interval that contains 1 without getting a point a teeny bit to the right of 1. Because I have to write a number here. I can't write 1 because then 1's not in there. So I need to write a number slightly smaller than 1. But whatever number is slightly smaller than 1 you choose, 1.001, well then half that number is inside the interval. So then 1.0005, that is half of that. Not half. The average between 1 and that. That's the middle point between that and 1. Anyways, the point is this number is inside that interval, and it's a little bit to the right of 1. So where does it map? It maps up here, which is always outside that epsilon.
What if you put the epsilon up above that so that it will then...
For any epsilon. Not for some epsilon, for any.
Oh, I see what you're saying.
Yes. For every epsilon greater than 0, there exists a delta. These are good questions. Help clarify things. Anything else?
Should we go?
Students.
I do see what you're saying. So if you're coming in from that side, no matter how small you get, you'll never make it to that point.
Right, so from this side, you're always going to jump clear up here.
Yeah.
Your other problem is you say, okay, let's not pick this point then. Let's pick this point to be my limit. Well, then you have the problem coming this way.
So now you have
Every
two
point on
answers.
this side includes points down here. So your interval's up here. You always get points down here. They're outside your interval.
So you have two answers depending on this, which direction you go.
Right. Those two
Wow.
answers conflict with each other. And we can't say, well, in some cases it's equal to this. In other cases, we're going to call it this.
Which there's two
Then it's not
outlets.
defined. You can't
Two
say an
outlets.
expression is equal to two things that aren't equal.
Mm-hmm.
Otherwise, you get contradiction in math.
Yeah, that makes a lot more sense. It's starting to click.
Cool. Good?
Yeah.
All right.